Hi, this is Sushant, and we are forward continuing our series of radioactivity. So, the very introductory video, our initial video, we talked about what actually radioactivity means and the idea about unstable nucleus and radiation. We categorize the radiation in its three types, that is alpha, beta, and gamma, and also we discuss in short about the instability of the nucleus. So, we discussed about the two key factors that defines the stability or the instability of the nucleus. One is the size of the nucleus will define the stability, and the another is the Zn graph, that is the proton neutron ratio inside the nucleus will define the stability of the nucleus. So we are going to discuss about the first one. So we are delve into the context of nucleus stability on the basis of their size. So how the size of the nucleus define the stability of the nucleus, and how the larger size nucleus automatically becomes unstable. So unstable nucleus or unstable nuclei. In our approach of understanding the instability or stability of the nucleus, we have to look inside the nucleus. So nucleus is composed of nucleons, that is the proton, which is positively charged, and the neutron, which is negatively charged inside the nucleus. They are fermions, or we can simply call it as the nucleons. So this nucleons particle, that the proton and neutron, which is inside the nucleus, define the stability. And how it is doing so? The positive charge and the proton and the neutron are composed of quark particles. So if we are enlarging the picture of a proton, we will see this single proton is made up of two up quark and one down quark, and the neutron, which is a chargeless particle inside the nucleus, is itself made up of two down quark and one up quark, and this quarks are possessing its own charge, which is up quark is acquiring plus 2/3 of electron, charge of plus 2/3 of electron, same as a down quark is acquiring minus 1/3 of charge of electron. So altogether, when we are adding up the charges of two up quark and one down quark, the proton is end up having a charge of 1 electron plus 1 electron, and the neutron is ending up having a charge 0. So it is not possessing any sort of charges. What we will do, we will add up the total charge of all the quark, all the ingredient quark that is presenting inside the nucleus. So we will end up getting the charge 0 for a neutron and the charge of plus 1 of electron for a proton. These quarks are binded with each other with gluons, and these gluons are the force carrier for strong nuclear force. These gluons, which is present in both neutron and proton, these gluons, which is present in both proton and neutron, that is binding of the quark, is the force carrier for the strong nuclear force. And what a strong nuclear force is? It is a short range attractive force. It is a short range attractive force which is 100 times stronger than the forces between the charges. It is 100 times more stronger. The strong nuclear force is 100 times stronger than the forces between the charges, that is the electrostatic force. So a strong nuclear force, which is 100 times stronger than the electrostatic force, is due to the gluons, that is binding of the quark particles. And from the idea of the gluons, we can say the proton and the neutron both are composed of the quark, and they are sticking up together with the gluons, so both are contributing to the strong nuclear force. This is the key idea for understanding the stability of the nucleus. Proton and neutron both are contributing to the strong nuclear force, but the strong nuclear force, that is sticking up all the gluons, that is sticking up the positive charge and the chargeless neutrons inside the nucleus, is a short range force, is an attractive short range force that is 100 times stronger than the repulsive force that will be present between these positive charge particles. And as we know that the electrostatic force between opposite charges is attractive, and the electrostatic force between the same charges is repulsive. And as the nucleus is itself possessing, itself containing the similar type of charges, that is the positive charges of proton, so there is a repulsive force between the charges inside the nucleus, and if the only repulsive force is in charge, the nucleus will fall apart. It won't be able to be in a very concentric narrow space, but we are perceiving nucleus as a central part of the atom in which the charged particles are being concised into a very narrow space. So how it is happening in the very first place, and how the size will define or alters the stability of that nucleus. So for the smaller size nucleus, the strong nuclear force is much more stronger or dominant, or a strong nuclear force between these positive charges that is being generated by the gluons are in charge, are in dominance than the coulombic repulsion between the positive charges, protons. Coulombic repulsion. So a strong nuclear force between the between these nucleons is stronger than the repulsive force due to these positive charges, as the strong nuclear force is a short range force. For short range force, that is, it acts from 1 to 3 femtometer. For a very small range, it is so much dominance, and it is 100 times stronger than the repulsive force between the charges. So it's obvious that the nucleus is stable, and it is in a perfectly equilibrium to consider it as a stable nucleus. But for a larger size atom, what actually happens is, for a huge size atom, when the atomic size becomes large, the positive charge or the proton, the positive nucleon that is at the very far end of the nucleus, will exert a repulsive force, as the coulombic repulsion is extended up to the infinity. So the repulsive force will act up to the infinity, but the strong nuclear force will act to the very short range. So when the size increases, the charges at the very opposite end are still exerting coulombic repulsion, are still exerting the electrostatic force of repulsion to the another charges, but due to this large distance, the strong nuclear force, the dominance of a strong nuclear force become minimal, or it reduces. So for the larger size atom, the strong nuclear force become ineffective in a way, and coulombic repulsion is in charge. And that's how the larger size atom, for the larger size nucleus, the nucleus automatically become unstable, because the repulsive force, it is compelling it to be spread apart, to be split apart, but somehow it is so hardly able to manage the shape of the nucleus. So what is the key motto of this larger size nucleus, the unstable nucleus? So it has to be somehow balance these forces, the by increasing the dominance of the strong nuclear force, and the dominance by depressing the dominance of coulombic repulsion. So how it will be done? How can a larger size nucleus, which is technically unstable in a way, now right now we can understood the fashion of these two forces that is defining the stability of the nucleus, and these two forces are directly related to the range, directly related to the size or the distance between the fermions, or the distance between the nucleons. So for the larger size, the nucleus at the nucleons, the positive nucleons, that is the protons at the very end, will still exerting the coulombic repulsion, but at the very farther end, the strong nuclear force, the dominance of the strong nuclear force is not so much active, then it becomes unstable. So now the idea of gaining the stability will be in such fashion. Now, the larger size nucleus, like 92 uranium-238, so obviously the nucleus will be massive, the nucleus will be huge, the coulombic repulsion will be very active in a dominant state. So it will, the main motto of this uranium atom, the uranium nucleus, will be reducing its size and balancing these two forces, balancing this repulsive, coulombic repulsive force, electrostatic repulsive force, and the nuclear force of attraction. So by the equilibrium, a balance, a perfect equilibrium of these two forces, nucleus will be, become stable, and that is the ultimate goal of anything in nature, will tends toward the stability. So what it will do, it will reduce its size, like we consider as an imaginary uranium atom, and these are the positive charges randomly embedded into the nucleus, and few sorts of nucleons, chargeless nucleons, that is neutrons, also embedded randomly into the nucleus. It's not so random, the orientation have some sort of meaning that we will discuss later. So I am not able to plug in the whole number of proton, the whole number of neutron into the nucleus, but we are just somehow estimating the idea how it is done and how it becomes stable. So its key motto is to reduce its size, and how it is done, it will emit an alpha particle. So what is alpha particle? We earlier discussed alpha particle is nothing but a helium nucleus which is possessing two proton, two positive charge, and two neutrons, that resulting in the weight of 4 AMU, resulting in the weight of alpha particle becoming 4 AMU. So after, by emitting the alpha particle, the charge of this nucleus will reduce by 2, and the mass of the nucleus will reduce by 4, because it has to some sort of emission, it has to do some sort of emission in which the two positive charge and the two chargeless neutron has to be reduced by the nucleus, has to be subtract from the nucleus, and what we are getting the nucleus with two less positive charge and 4 less nucleons, and resulting the diminution, the minimizing the size of the nucleus. So in the process, one thing we have to focus on, that the alpha, by the emission of alpha particle, the size become smaller, but what we are getting, the diminished size of the nucleus, what we are getting after the emission of the alpha particle, is not uranium. So whenever we have to differentiate, distinguish, or whenever we have to categorize the element, we are categorizing, we are defining element on the basis of its atomic number, or on the basis of its proton number. So when it is said it's calcium, what the first thing that should come to our mind is there must be 20 proton inside the nucleus. That is how we define the element. So when someone says it's sodium, the very first thing that came to our mind is there are 11 proton inside the nucleus. So the proton number, the atomic number, defines the element. So when the uranium emitted alpha particle, its charge is reduced by 2, because 2 positive charge has been emitted. So after deduction, there are 19 proton, and then 19 proton is not uranium but thorium. So it will become thorium. And the mass is also reduced by 4. So from 238 it becomes 234. And how this is how the nucleus, unstable nucleus, is becoming stable. Becoming stable means not absolute stability. The thorium 234 is more stable than 92 uranium 238. It is more stable, but not the absolute stability it already acquired. It has to go through the multiple stages of this radioactive emission to gain the absolute stability, from where you do not have to go under any type of radioactivity or radioactivity decay, radioactivity disintegration. But one thing we should focus on, the thorium is itself a radioactive nuclei, but it is more stable than the uranium 238, 92 uranium 238. So again, it is possible that this thorium will further disintegrate into, after emitting an alpha particle, it will further disintegrate into radium. So this thorium is emitting an alpha particle and becoming radium, and the radium is also radioactive nuclei, unstable nuclei. Then again it will undergoes alpha decay. So in all this process, this nucleus are emitting alpha particles. So such type of decay are considered to be alpha decay. Such type of decay is alpha decay, and it will become radon. And it again its charge is reduced by 2 and mass will be reduced by 4. Few things we have to focus on is, for the very first thing is, so if this is also radioactive, but the stability is more than the uranium. Radium is also radioactive, but the stability is more than that of thorium. Radon is also radioactive, but the stability is more than that of radon. So we can say the very after the very next step, the stability of the nucleus become more and more. And one thing that might come to our mind, that why the uranium at the very first stage emit 2 or 3 alpha particle at the same time and directly become radium, so radon, which is much more stable than thorium or radium. So why it is not doing so? It is a compulsive process. It is a stepwise oriented process in which the uranium or any radioactive element can emit only 1 alpha particle at a time. So like as we are studying in a anyone is doing graduation, so no matter how brilliant you are, you cannot study first year and directly went to the 4th year. If the bachelor course is a 4 year, you have to be in the 2nd year, you have to be in the 3rd year, and you have to be in the 4th year. So that continuous fashion scenario should can't be break by any means. So no matter by emitting how much alpha particle, it will gain a perfect stability, it will gain a much more better stability. It can't do it at once. It has to go through multiple phases. So in alpha decay, one unstable nucleus can emit only 1 alpha particle at a time, and become more stable than the earlier version. The earlier unstable nucleus, it will become more stable, extended, but it can emit one alpha particle at a time. And by doing this for the multiple time, by the multiple dimensions of repetition, it can gain more and more stability at a time. So we discussed about the instability of the nucleus and how the instability of the nucleus is size oriented, and on the basis of the size orientation, a nucleus will emit an helium nuclei, or that is alpha particle, and it become more and more stable, and such process is called alpha decay. And for the coming video, we will be discussing about the instability of the nucleus on the basis of ZN graph, on the basis of proton and neutron ratio. Thank you.